And let me introduce Dr. Thayne Currie, everybody. Thank you for joining us on the show. You did come from University of Texas at San Antonio, but I know you from the Twitterverse, and there were some posts about exoplanet imaged, baby exoplanet forming in an unusual way. This proves it, all sorts of different levels of clickbait. And I had noticed you had chimed in at one point strongly in the side of the camp saying, look, this thing's probably real. Enough folks are seeing it. It's been confirmed enough times. We need to be thinking of this rather than just a possible, blob, that maybe there's something really there. But first of all, I thought instead of me trying to go reproduce all of that, let's just invite you to the show. So here we are tonight, finally getting to talk about that object. And thank you so much for joining us to be able to tell our audience about some real research that's going on about imaging exoplanets. So welcome to All Space Considered.
Well, thank you very much. And I'm very happy to be here. So I'm very excited to talk about the work that you just alluded to. So I'm going to be focusing on work that we published recently in Nature Astronomy on trying to image planets around other stars, specifically image planets still in the process of forming around other stars, and what this tells us about the diversity of planetary systems that the universe can spawn, and how the solar system is common or unique. And also, just as a preface to this, if you do have questions during the course of what I'll present, go ahead and chime in and interrupt. It's totally fine. It'll be a lot of fun that way, I think. So to kind of give you this kind of step back a little bit, in the past 30 years, we have identified now over 4,000, I forget how many now, over 4,000 planets around nearby stars. And these span a wide range of properties. So over a factor of 100 difference in size and in orbital period. Okay, now only a subset of these are planets that we can image, and they actually end up being really interesting in terms of understanding how our own solar system fits within this sort of broader context for planet formation. So here's an example of some of these directly imaged planets. These are all fully formed directly imaged planets. The one on the left, this is the first directly imaged planetary system. This is HR 8799. You're showing, so you're seeing a movie of the planets orbiting all counterclockwise in this image. And these have been studied for since about 2007, 2008 or so. And then we've identified about another 24 or so directly imaged planets. Now, what's really interesting, I think, compare what these planetary systems look like to the planets in our own solar system. So if you plotted the size of the solar system compared to the scale of these planets orbiting their host star, it's very different. So this is one of the most solar system-like directly imaged planetary systems that we know about. And still, it's all of its planets orbit at very wide separations. So the outermost planet is about 70 astronomical units, like maybe about twice the distance between the sun and Pluto, typically. So these are extreme systems, and not only are they very far away, they are planets that are massive. So over 5 times the mass of Jupiter. So how do we form these planets? And so that's really going to be the focus of what I'm going to be talking about. And to really understand that, we need to sort of bridge the gap between the starting points and the end points for planet formation. This is an example of the Pillars of Creation image from the James Webb Space Telescope. You see these beautiful filaments. These are sort of the nurseries for stars. And if you look at some of these stars up close with, like maybe the James Webb Space Telescope or the Hubble Space Telescope, you can see these features, these sort of silhouettes of disks of gas and dust surrounding them. So these protoplanetary disks provide the seed material for planet formation. And so this is the material from which, for example, in our own system, from which Jupiter, Saturn, Uranus, and Neptune, and all the solar system planets form. So if we want to understand how will we go from the starting point to the end point for a fully formed planetary system, we need to look at stars surrounded by protoplanetary disks that appear to be incorporating appear to be actively incorporating their material into planets. Maybe this be identified by different structures in these disks that are telltale signs of planetary systems. And we have a lot of these examples now from the best telescopes on the ground in Hawaii and in Chile, and also sometimes in space with HST and hopefully soon JWST. And we see evidence for these wide range of structures, where they may be cleared cavities, spiral arms. All these, we think, are good telltale signs that that protoplanetary disk is starting to incorporate some of this material into a planet. And so then the challenge then is to actually image systems where we detect both the protoplanetary disk and the planet. So we're actually seeing this process of planet growth happen in action. So one of the archetypical systems for this is a star called AB Aurigae. So this is in the Taurus Aurigae star forming region. This is maybe about like a couple of million years old or so, depending on who you ask, about 2 to 3 million years old. It seems to be sort of the consensus opinion on how old the star forming region is. And this is an amazing system. So if you compare the orbit of Pluto to the disk that we resolve even with very old Hubble Space Telescope data, we see that this disk, this protoplanetary disk, is enormous, stretching out many, many times larger than the distance between the sun and Pluto. So hundreds and hundreds of astronomical units. This is an enormous disk, and also is very massive, we think. And if we look a little bit closer at AB Aurigae, we do find evidence that it does seem to have these sort of features in it that may be evidence for planet incorporation, of planet growth. So in the early 2000s, we first identified evidence for spiral arms in the disk around AB Aurigae. You see a couple examples of spiral arms on the image shown at the far left. If we look a little bit closer, so this would be a little bit more on solar system scale. So maybe about 5 times to 20 times the distance between the sun and Jupiter or Saturn. We see even more structure. We see this really weird feature, actually. It almost looks like a baby Godzilla. And so it seems like there's a lot going on in this disk that motivates us to look further. Now, the images on the far left and the middle left, those are in the near infrared. So they are about maybe 1 to 2 microns. They probe very small dust. If we look at other wavelengths, we can see additional telltale signs that this disk is probably incorporating some of this material into a planet somewhere in this disk. Specifically, if we look at pebble-sized dust that's probed by, for example, the Atacama Large Millimeter Array in Chile, we see these two features. If we look in gas, we see additional spiral arms, specifically in carbon monoxide. If we look in dust, we see this cleared cavity. Now, both of these we think are telltale signs of a planet that is clearing out the dust in this disk and is launching or is connected to these spiral density waves in the disk. Okay. Also, AB Aurigae is a film star. So while the paper upon which we focused our result on was under review, this movie, Don't Look Up, as I'm sure many of you have watched, came out. And actually at about the 2 minute 15 second mark or so, you can actually see an image of AB Aurigae in this movie and actually see roughly the location of the protoplanet that I'll be describing in a few slides. So this is great. We have this really interesting system. We want to look a little bit more carefully to be able to see whether or not there's evidence for a protoplanet a little bit more directly, not just simply looking at features of the disk. And so to be able to do that, we need to get extremely sharp images of this system and be able to separate out light from the star and light from the disk and from the planet. So if we want to do this on a ground-based telescope, we needed a very advanced, what's called an adaptive optics system, to be able to rapidly correct for blurring of starlight due to the atmosphere, even on the best sites. So we use the Subaru Chronographic Extreme Adaptive Optics Project, or SCEXIO for short. This is an AO system on the Subaru telescope on Mauna Kea. It uses a very advanced sensor to be able to figure out exactly how the atmosphere is blurring starlight, and then uses a small deformable mirror with 2,000 actuators to be able to correct for that atmospheric blurring over 2,000 times a second. It's able to get extremely sharp images, and we quantify this in terms of a quantity called the Strehl ratio, which basically means we get extremely sharp images, about 90% of the theoretical maximum sharpness we can possibly get. So then we feed the sharpened starlight to a suite of science instruments. The two that are going to be focusing on are an integral field spectrograph in the near infrared. So basically what this means is that you get a bunch of different images at all these different wavelengths simultaneously. Then you also have an optical instrument to be able to get images of the system in visible light. And we assist our program with Subaru using the Hubble Space Telescope. So that was launched many, many, many years ago, but it's still quite powerful. And we're able to complement our Subaru observations, looking at a slightly different range of wavelengths, and also looking at a data taken over a 20-year time span. So this is the image that we get. So the left, what we see is a composite image with SCEXIO. So our actual data is in blue. And the image from ALMA, which is probing on the pebble-sized dust, that's in red. So we're seeing composite image. So we see this bright blob here, is denoted by a green arrow, almost due south of the star, lying interior to this ring of dust. Okay, and that in a sort of a protoplanet or source lying interior to a cleared ring, that's roughly what you expect for a massive planet causing the clearing of this ring. And furthermore, if we try to actually model where we might think a planet would be to be able to explain those CO gas spirals, there is one predicted position for this that is dead on exactly where we see this protoplanet, almost due south. The image on the right shows this system in a little bit more dramatic fashion, where we used a little bit more advanced processing, and we scaled the image intensity by the distance it is from the star. And so you can see the AB Auriga B, as we call this protoplanet, is this bright blob that appears to be sitting on this very complex structure of the protoplanetary disk. We see all these different spiral patterns. Okay, and if you compare the size of, the distance that AB Auriga B is from the star, this is a very wide separation. So look at the little small inset region. That's the orbit roughly of Neptune. Okay, so we're about 4 or 5 times further away from the star than Neptune is from the sun. So we also have HST data, and this ends up being very important because, if you have a planet very far from a star, it orbits very slowly. And sort of to really tell for sure that we're seeing an orbiting object as opposed to a static feature, we need to monitor this system for a very, very long time. Now, for this particular star, it means we would need to monitor this star for over a decade. Thankfully, we don't have to wait a decade in order to be able to confirm this object. There were actually archival data for AB Auriga taken in 2007 that we reduced, and we got a detection of this protoplanet. We obtained new data with the Hubble Space Telescope in winter of 2021. Now, if you look at the vertical line in this image compared to the position of AB Auriga B, you see this appears to be shifting in its position. So it appears to be consistent with roughly what we expect for counterclockwise orbital motion. Okay, so this appears to be a moving object, which is kind of what we expect. Another key test we want to make is we want to be able to tell for sure that this source of light is different than the light we would expect from a pure protoplanetary disk feature that has nothing to do with the planet. Now, there are a couple of different tests we apply to be able to do this. So the first is that if we're seeing just scatter light from very, very, very small dust in a protoplanetary disk, that light will be visible in what's called total intensity, so normal scatter light, or polarized intensity. So we're only looking at polarized starlight. But if it's a planet, we would expect to see this emission in total intensity, but have only a weak signature or even a non-detection in polarized light. So if we compare the total intensity image of AB Riga B on the left to the polarized intensity image in the middle, we do see that B lights up in total intensity, but is basically featureless as a non-detection in polarized intensity. So that's good. The other thing we would expect is that if this is a growing protoplanet, it should be, or might be, accreting. And we think we have good ideas of what the signature of that accretion should be. If it's like a star, it would be accretion that would show up very clearly at what's called the H alpha line at visible wavelengths. So we obtained data with Skexio in the H alpha line, and we see this detection very, very convincingly. So those are two very, very key lines of evidence. We also see that its emission appears to change as a function of wavelength as we go from about 1 microns to about 2 microns, which is the range of wavelengths we use to be able to study this system with the Currie system on Skexio. It appears to actually be a lot harder to see. It gets a lot more confused with the protoplanetary disk at longer wavelengths, but it really pops out at slightly shorter wavelengths at about 1 to 1.6 microns. In fact, if we compare its spectrum and its photometric points, so those are shown in magenta and those are shown in green, to models for what we expect for like a circumplanetary disk or an accreting object, and also models compared to what we expect for a sort of a scaled down star, scattered starlight, we see that it can be reproduced by about a 2000 for about 2500 Kelvin. It should be, that's a typo on the slide, about 2000 to 2500 Kelvin thermal source, and then a very hot accreting source of emission. Now, this composite itself appears to be inconsistent with what we expect for scattered starlight. So how massive is this object? Well, we think if we compare its luminosity to models for planets that try to map planets as a function of luminosity, age, and mass, we think this is most consistent with the light we'd expect from about a 9 to 12 Jupiter mass object. So this is really, really strange. This is about a 9 to 12 Jupiter mass planet orbiting at a distance 20 times the distance from the sun to Jupiter. So how did that object form? And this is where the broader significance of this result really gets to, really kicks in. So here's AB Riga and the detection of B. That is the solar system on the scale of this image. So again, we're seeing this very massive, wide separation object. How do we think that formed? Well, if it formed like things like like Jupiter and Saturn in our own solar system, it would have formed by core accretion, where you start with very small dust that builds up to pebbles, then to boulders, and then once you have cores that become roughly about the mass of several times the mass of the Earth, they undergo runaway gas accretion, and they're able to suck up all the gas surrounding them, and they end up building up the envelopes of gas in Jupiter and Saturn and other gas giant planets. Now, this works very well up to a few tens of AU separation. But AB Riga B is at almost 100 AU separation. It's very hard to imagine how this particular mechanism would work to be able to explain what we see. Now, there's an alternate mechanism which had been long sort of challenged or almost discarded, I would say, called disk instability, where the initial protoplanetary disk is so massive it undergoes rapid collapse and pieces of it fragment at a time. Now, this works conversely very well at wide separations at about 100 AU, so roughly where we expect, so actually roughly where we see a protoplanet in the system. And in fact, if you do perform models of planet formation by disk instability, there's a range of initial conditions for planet mass that overlap roughly with what we think AB Auriga's protoplanetary disk might be, that will end up forming at least one or maybe even a few more planet mass fragments. So that's our result. We think that we found evidence for Jovian planet formation at a wide separation, a very massive, maybe about 9 to 12 Jupiter mass object, about 20 times the distance between the sun and Jupiter, that may have been formed in an entirely different way than any of the planets in our own solar system. And we'll see what we learn later with future observations from the ground and from space.
Thank you so much for that. That's super interesting to see the fragmentation like that happening. One of our folks in our chat wanted to know how having such a massive planet so far from its star, how would that affect any planets that might be closer in that we're not detecting yet? How does having a massive planet out there, how does that affect their evolution?
So that's a good question. And so at least I think it's probably easier to answer that question with the context of planet formation in our own solar system, where Jupiter's formation affected the asteroid belts and perhaps affected the orbital configuration of the innermost planets. There really hasn't been a lot of, to my knowledge, a lot of detailed studies on how a very wide separation massive planet formed by disk instability would have a practical consequence for planet formation at smaller separations. In a lot of these models, what we find is that these planets end up migrating. So a planet may be formed at 100 AU, may end up migrating inwards or outwards. So that may complicate the formation of maybe rocky planets in the solar system. But there's really a lot to work through with this type of system. And to really be able to motivate yourself to conduct that study, it's good to have examples of planets formed by disk instability. And this is a new result. And so we just maybe have not seen the type of work necessary to be able to answer that question.
Okay.
It'd be very interesting to see that.
Yeah. Do you think it's typical to have a protoplanet that's so far away from its star, based upon what you've seen? That's another question coming from our audience.
Great question. So the easier way of answering that is we do have a good sense of the frequency of fully formed planets at these separations at about 100 AU or so. That frequency is very low, maybe a few percent at most. Okay, so at least tens of millions of years after planet formation ends, there doesn't seem to be very, very many massive planets at these types of separations. So this may be an extremely rare type of object.
Okay. Very interesting. Chris or Patrick, did you have any questions before I turn back to our audience one more time?
Gosh, I sure do. The designation AB, if I'm remembering right, is a variable star designation, or does it have a companion?
It doesn't have a stellar companion that I'm aware of, and that is in the literature. No.
I was wondering if the presence of a companion might have an impact on the material around a star and encourage or discourage rapid collapse planetary formation.
So I'm a little bit unsure of exactly what would happen for a binary star. What would happen with that for forming a planet at sort of like intermediate distances around gravitational stability? I imagine it would complicate or suppress that method. But what we do know, what we do have some good confidence in, is that medium separation binary systems. So, where the separation between the primary and the secondary is maybe the distance between the sun and Jupiter to the sun and Neptune. Those types of systems seem to be well correlated with a reduced frequency of protoplanetary disks. So it either means that that planet formation in those systems operate very rapidly, or that the entire process is suppressed. And I suspect the latter is probably the more likely scenario.
So is there any evidence of planet breakup and forming kind of asteroid type belts in these regions that have been seen, and could this shed light on how our own asteroid belt could have formed?
Great question. So in this particular system, in AB Riga, the disk has some cavities or some gaps, but it's still at the kind of an early stage to have a sort of like a classical asteroid belt or a Kuiper belt, like this two belt system that we're familiar with in our own solar system. We're at a little bit of an earlier evolutionary stage for that. There are other systems though, including possibly HRA 799, that fully formed planetary system, which have both an asteroid belt and a Kuiper belt analog in the system. There are a number of systems that do have that. Yes.
When you see these sorts of objects forming, even if it is a super, super rare one, what do you think might be next? There's got to be a reason you keep going back to image the next one. What are you hoping to find? Just curious, what's your white whale out there, I guess, in terms of imaging an exoplanet?
Okay, so I think there are two answers to that question. So one is, what is the goal? What's sort of the immediate goal for this particular focus with studying planet formation, and then sort of the broader goal for direct imaging in general. So with the first, I think what we're seeing with AB Riga and then with the other system with directly imaged protoplanets, so that's PDS-70, we're seeing like this sort of like the low-hanging fruit of planet formation, the easiest systems to be able to image. These are not typical systems though. So if we want to be able to study planet formation on a little bit more solar system scales, so like planet formation on a true sun to Jupiter separation, we need more powerful adaptive optic systems and eventually larger telescopes on the ground, like ELT, TMT, and GMT. And then in space with a future flagship mission. So those may be able to give us, reveal this hidden population of growing planets. And so it may actually reveal systems that are a little bit more typical. AB Riga is a star 2 times more massive than the sun. Its disk is extremely massive. Most stars are less massive than the sun. Their disks are less massive than AB Riga's disks. So as we get more powerful capabilities, we may be able to probe systems that are more representative of the typical system that forms. Broadly speaking, though, with direct imaging is that eventually we want to get to the point where we can image an Earth twin around a nearby star, whether it be around a sun-like star or around a low-mass star. So again, the types of systems that we are imaging right now that are still in the process of forming, these are a very mild contrast, meaning that the planet is fainter than the star significantly, but only 10,000 times fainter than the star, or only 100 times that, 100,000 times fainter than the star. To be able to image an Earth around a low-mass star in the habitable zone, we would have to be able to image ones that are 100 million times fainter than their host stars. That's a lot more challenging. So that we require new technology to be able to get us to that point. And then new technology in the process will help us study planet formation.
Do you think it's possible? Is
Yes.
This reachable within how many decades off is it? Or are we waiting another 10 years or 20 years, or what do you
I'm an optimist on this, mostly because I see this as an engineering problem, not fundamentally as a physics problem. that if we had, if we had the budget of the U.S. military, this could be done with fairly expediently. On astronomy timescale, right? But I think realistically, this will take this will take more than a decade from now, maybe 2 decades, to be able to get to that point where we're really starting to look at true Earth analogs around nearby stars.
Yeah, we want to see blue oceans and white ice caps, along with maybe some brown and green continents. That would be certainly a thrill.
I was going to mention I came across a project and it's part of the NASA NIAC proposal of sending a telescope out to about 540 AUs and using the sun's gravity field as a lens to image planets. And I don't know if you've heard of that and that project.
I've heard of it. I don't know the details for that. I mean, my focus has been largely on the capabilities that are upcoming on the ground, and then the Roman Space Telescope as a springboard, then to be able to image an Earth around a sun-like star with a flagship mission.
Yeah.
But that is an interesting idea. I don't know how feasible it is, but an interesting idea.
Yeah, there's there are more revolutionary telescopes coming for us to play with, which is very exciting. JWST has really shown that it's working as it was designed. It's working better than designed in some ways. But we've got the Nancy Grace Roman coming. We've got there are exciting times about taking some being able to do surveys with large populations with wide field of view. Andromeda in just a couple of pointings, I think it is. It's 1 or 2 pointings to do the bulk of Andromeda, which is crazy. So yeah, anyway, some fun stuff to look forward to for sure.
Yeah, it's an exciting time for sure. And even beyond that, I mean, the Subaru telescope is 20 years old, but it was still able to produce this result because we can keep upgrading and enhancing the telescopes we do have. So yeah. there's a lot at our disposal for sure.
Just because I know our fans like them, you were using adaptive optics. Were you shooting lasers out? Were you using laser adaptive, or was it
no? I wasn't using laser guide star adaptive optics. I was using natural guide star adaptive.
Okay. So you were only where other bright stars were located.
Exactly.
Okay. Well, maybe we'll let you come back onto All Space Considered after you've used some lasers.
I'll see what I can do about that.
I kid, of course. This has been an amazing insight into hunting for exoplanets, hunting for direct imaging. This isn't just, I believe spectroscopy. I believe the wobbles in the lines. But still, there is something super exciting to seeing an image and seeing a blob there, and then seeing an image taking a handful of years later, and that blob has moved in the manner you'd expect it to move when it's a planet. That's the stuff that dreams were made of when I was a kid. So I find this stuff to be incredibly exciting, and really do look forward to all the advances that are going to be made in this.
Seeing is believing.
Yeah. Absolutely.
Exactly.
Absolutely. So thank you so much for sharing your the sites you're seeing, and we very much appreciate it.